Hi everyone and welcome to today's SemActive online training session. So today the topic of my session will be how to efficiently process satellite imagery within Correlator 3D. So as a lot of you may know, satellite imagery really differs from aerial imagery. So today the goal of my presentation is to show you the workflow on how to successfully process your satellite imagery in Correlator 3D. So satellite imagery, as I just said, differs quite a lot from aerial imagery and have many advantages compared to aerial, such as the areas that you can map with only one scene. Also, it can bring much more information in other wavelengths that we don't usually see within our eyes because of the multispectral band that satellite imagery can allow us to have. However, there's a few cons that comes with the satellite imagery, such as it's really cloud sensitive. So clouds are a big challenge when using optical imagery, especially satellite, since they're taking way far from the Earth. Also, the resolution is a bit more coarser than what we have for aerial imagery or UAV. And I will talk a bit about that during this presentation. And also the cost related to the acquisition of those satellite imagery. Even though there's a lot of new satellites these days, it's still quite expensive to acquire good satellite imagery for photogrammetric processing. So before jumping into this session, I would like just to introduce you to the what we call the three types of resolution that we can find in satellite imagery. So we have what we call the lower resolution satellite, which has resolution of 60 meters and more. Those are usually freely available data and gonna give you neutral information about the sites. We also have what we call the medium resolution satellites, which is maybe from 30 to 10 meters resolution. In this category, I would include Landsat satellite and also Sentinel satellite. Those are usually monospectral acquisition that's going to give you, let's say for Sentinel, a 10 meters resolution imagery, depending on the band you will use. But again, those are freely available imagery. And the other type of imagery, which we're going to use for photogrammetric processing, is what we call the high and very high resolution, from maybe 5 meters to 30 centimeters, depending on the satellite you will look at. So today, the goal of this presentation is really going to be focused on the last category I just talked. So I'm going to talk a bit later on about few satellites that you can use for photogrammetric processing in Correlator 3D. And also, basically, the usage of satellite imagery can be multiple. It can be used in geology because of the different spectral band. Also in vegetation analysis, since we know that vegetation have an effect in the non-visible near-infrared spectrum. Also, it can be used for hazard monitoring, since we can collect quickly data over the same area, and also it can be used for land use analysis. So today what you will learn for this presentation, so I will start by presenting you the overall workflow of processing satellite imagery. Then we will talk about preparing input data and pairing images for Correlator 3D project. Then we will talk about refining the RPCs through the aerial triangulation, generating high-resolution DSMs and DTM, producing orthomosaic, and then finally Pansharpening of multispectral imagery, and we will finish with a session of questions. So now let's start with the workflow for satellite imagery. So basically, the workflow is quite similar of the aerial project within Correlator 3D. Maybe the first few things that will change is for the project creation and also at the end for the Pansharpening of the multispectral imagery. So first of all, the first step is to create your project and also pair your images to successfully create a surface model from your panchromatic images. I will talk later a bit about the difference between the multispectral and the panchromatic and their each resolution. Then, once you have created your project, you can proceed with your aerial triangulation, such as in 2 steps, with the tie point extraction. And then you can also add checkpoints or ground control points to refine the overall accuracy of your model. And then you will be able to refine the rational polynomial coefficient of your satellite pair imagery. From there, you will be able to extract a surface model and a terrain model from those images, which you can also do a few editing on it. And finally, from this surface model, you will be able to ortho-rectify your images. And depending on the number of images that you have, if you have a multiple scene image, you will be able to create a mosaic of those images. And finally, if you only have one images or you have a mosaic, you will be able to Pansharp the multispectral imagery. So let's start by preparing the input data for your Correlator 3D project. So basically, what are the input requirements to do photogrammetric processing with satellite imagery? So basically, there's 2 things that are necessary. First of it is the images itself, and the other is the RPC. So the images can be stored either in 8 bits or in 16 bits without any issue. And depending on the satellites or the order that you had, you will have the option of which one. And we usually require the panchromatic bands to extract the surface model because the panchromatic band is known to have a finer resolution, which is gonna have more details than the multispectral one. So usually what we're gonna do is we're gonna create a project. If you have access to both imagery, so multispectral and panchromatic, you will need to use both, but the surface model will be extracted from the panchromatic imagery. And the other thing that we need is we need basically the rational polynomial coefficient, commonly known as RPC file. The RPC file can come as an XML file depending on the provider that you have acquired your image from, or let's say from Digital Globe, they could come within a file that has the extension .rpb. So basically, what is an RPC? An RPC is a compact representation of the ground to image geometry. Usually the satellite provider is going to give you this information because they don't want to give you the real physical camera model behind the satellite. So it's gonna it's necessary to have the RPC file to be able to extract or to rectify a satellite imagery within Correlator 3D. Also, another element that's quite important when you want to do photogrammetry with satellite imagery is there's 2 types of acquisition that maybe you're not too familiar with. So we have what we call the in-track stereo, which is basically when the images are acquired on the same orbit. So the satellite's gonna fly over the area, it's gonna scan the first images, then it's gonna rotate over a point and then scan the same scene from a different angle. So this really reduces the difference between the 2 imagery, and it's a key element to have successful surface model extracted from your satellite imagery. Also, we have what we call the cross-track stereo, which is basically when the images are not taking onto the same orbit. So maybe the satellite can take one images within an orbit, and then on the second orbit to the same scene, he's going to take the other imagery. However, those what we call cross-track stereo are less valuable for photogrammetry because they have much more difference between the images, and since the goal is trying to match pixels of each images together, when we have a lot of difference between two images, well, it can be a big challenge and might have an effect on the overall result you can get from it. So basically, what satellite correlator 3D can support. So correlator 3D can support many satellites as long as you have the image file stored in 8-bit or 16-bit and the RPC file that is attached with this satellite scene. So we can support satellites such as WorldView 1, 2, 3, and 4 if you still have data from this satellite. We can also process Pleiad satellite also from stereo or also tri-stereo capacity. So if you have the 3 images of the same scene, you can process those scenes within correlator 3D. We can also process satellite from spot image from spot, and also from ComSat satellite. There's many more. I've just here mentioned the most important one that we usually have more requests for. But if you have other needs, feel free to send us a request, and we'll see how we can help you with your photogrammetric processing. So now that we've known and we've talked a bit about the input data requirements, let's jump into the subject of today's training session. So how to create your project and pair your images. So basically, how to create a satellite project and how to pair your image satellite together. Here you will need, if you have access to your panchromatic and multispectral, you will need both of them. However, if you only have access to your panchromatic imagery, it is fine because you will be able to extract a surface model out of those. So basically, the project here creation is quite a bit different from the typical aerial project. So let me jump into how you can create your project. So here you have basically a window of correlator 3D, and you can see the visual interface. So when you want to create a new project, you will have to go into File and to New Project. So basically, here you will have a window like this that will appear, and it's gonna ask you to select what project type you want to do. So you're gonna select the satellite section. And then you will have a window like this, and you will be able to specify the RPC file. Note that here, when I will specify the RPC file, it will automatically retrieve the image file because the naming of the files are corresponding one to each other. So if I load here, as you may see here, so I have 2 folders. The first one is the panchromatic, and the other one is the multispectral. So the first step here is I will load in my multispectral imagery. So I will open this folder, and as you can see here, I have the first RPB file and the other RPB file. So I will load the first one like this. I will add it to my project. I will do the same thing with the other one like this. And then I will add both panchromatic images to my project. So I will go back into my panchromatic folder. I will load here the first scene, and then the same thing with the other one. And knowing here that I have four different images. So I have here the 2 M2As that are ortho ready stereo acquisition. For the M means multispectral, and the P here are panchromatic. So I have both images here. Then I will be able to pair my images together. So here, when you're going to pair your images, it's important that it's only going to be the images that you will use for the DSM generation. So since here we don't want to use our multispectral imagery for our DSM generation, since they have a coarser resolution than our panchromatic images, we only want to pair together our panchromatic images. So what you can do here is you will select the first images, which is the panchromatic, and then the other images. So I can see here that the numbers are not similar, are not the same, which means that are not the same images. In the case here where you would have, let's say, Pleiad tri-stereo, you would need to pair, let's say, the image 1 with the image 3, the image 1 with the image 2, and then the image 2 with the image 3. So you would have more than pairs, and all those pairs will be added together when we're going to generate the surface model from it. And also, tri-stereo is probably known to have a bit more accurate result because they reduce the occlusion that we can find from a satellite scene, because the same point is seen has more chance to be seen at least from 2 point of view. So you're gonna be able to extract a 3D coordinates from a specific point. So when those images are added together, the software is going to tell you that some of the images are not grouped into pair. You can say yes because we don't want to pair our multispectral imagery. And then finally, you will need to specify your project projection. In this case, we will use a UTM known zone. So we're going to be using WGS 8433 North. And also you will be able to select the location of your project folder. And if you have access here, you can load in a DEM file or a reference ortho as ground reference, or later on you can import a text file with GCPs and checkpoints if you have access to it. So now that we have talked about pairing images and project creation for satellite imagery, let's jump through the refining RPCs through aerial triangulation. So basically, the aerial triangulation can be broken down into multiple steps, minimum 2 steps, maybe 3 steps, depending on your requirements. So the first step is to do the type point extraction. So the software will find common features between your images and try to have a good relative accuracy between your scenes, and try to find a good geometry to match pixels together. Then, if you want to retrieve or you want to have a better overall accuracy of your overall photogrammetric model, you can add some ground control points and some checkpoints. So basically the difference is that the ground control points will be used during the bundle adjustment to refine the RPCs, and the checkpoint will be there to assess the overall accuracy of the final bundle solution. But they won't be used to do the calculation of the bundle. They only going to be used as a validation source. And finally, you will be able to do what we call the bundle adjustment. So we're going to refine the RPCs based on the type points and on the ground control points that we have found. And finally, what you've done, once you have done your aerial triangulation, you will be able to review the AT report to make sure that you have access to that you have good aerial triangulation solution, and your AT meets your accuracy needs for your specific project. So now, if we see how it looks within Correlator 3D, so basically here on the top of your screen, you can see all the different modules. So basically, the modules are in a sequential order from the automated workflow, which is going to be a one-click button solution, to the 3D to the mosaic creation. So basically, the first model here will be the aerial triangulation. So when you launch the module, the first time you're going to launch this module, you're going to have a window like this that will appear, and it's going to ask you, what type of type point extraction you want to perform. So always important to start with a standard extraction. And if you see that the software is not able to find common type points, you can then jump to an exhaustive extraction. But always start with a standard extraction, and you should have pretty good results from there. So once you have done the type point extraction, you will have here, those little two dots here that correspond to your specific images with the yellow square, and then you can display the type point that the software have found. So if I take out the base map here, so you can see that those little green dots here are common features that the software found between the images. Then, if you have access to ground control points or checkpoints, you can then import your ground control point as a text file here and specify their projection, their types, or you can also add them individually by marking them here in your project tree. So as you will see here, you will have all your ground control points here, and if you want to edit them, basically you can type in here the coordinates of the ground control points. You can also specify individual types for the point, so you can set this point maybe, let's say, only at elevation GCPs, planimetric GCPs, 3D GCPs, or as a checkpoints. And then you will be able to tag your specific ground control points. So here you will have a ground control point that we have found in the middle of the soccer field. But I've taken other ground control points which are like well spread out throughout the scene. So they're in the corner, most of it, of the imagery. So I'm making sure that they're not too close one to each other in order to have a good adjustment over the whole scene of my satellite project. So once your ground control points are tagged, you can then here generate the bundle adjustment. So feel free here to leave this parameters as they are now. The only option that you can probably change is here the ground reference. If you're gonna use a reference ortho or reference DEM, you will have the option here to use this specific parameters. But in this case, I will leave it as ground reference since I'm using ground control points. So now, once you have generated your aerial triangulation solution, you can also review the AT report, which is going to give you much more details about the final solution that the software has found before extracting your surface model from the images. So as we're going to have here, you will see that the software will display what we call a small quality report here. That's going to give you the average GCP's residual error, and you're going to have much more information about the overall adjustment that we have done on each of those images, the summary, so the number of type points, and also more information about the GCP summary here, same thing about the type points, and then you can also see we're going to provide you much more information about the overall solution, such as here the file that I've just shown you, but you're gonna also have information about the GCP. So if you want to troubleshoot, or if you want to see if there's a GCP that has a higher error compared to the other one, you can look at those files. You can have more information about the images adjustment that we've done and about the type points that we have found between the images. So now once you have done your aerial triangulation, you're ready to generate the surface model and the terrain model. So first of all, what is the difference between DSM and the DTM, what we call typically? Well, the DSM is what we call the digital surface model, and it's a representation of the overall content that you see on the images. So it's a model that's going to represent everything from the topography to everything that's also above the topography, such as houses, buildings, cars, and trees, and all the other elements. And the terrain and what we call the DTM, or the digital terrain model, is a representation of the Earth topography without having anything on the ground. So it's only going to be elements that are related to the topography. And here, there's many ways to extract terrain model from surface model. Maybe some of you have already worked with LiDAR technology. So LiDAR can give you a really high details terrain model. But for this purposes, we're gonna be able to extract the terrain model directly from the surface model with an algorithm that's gonna try to remove much of those buildings, cars, and all those other elements. So in Correlator 3D, the first step will be to generate a surface model from the input imagery, as we can see here on the right side of your screen. Also, when we worked with panchromatic and multispectral imagery, managing the image resolution, so what is the final optimal resolution you can get from the satellite imagery? That's always a good question. I usually suggest customers to go with a resolution that is fairly consistent to the resolution of the imagery. So maybe if you're working with maybe 30 centimeters imagery, you can go maybe a one-to-one matching, but you're gonna have much more noise than expected into the output. So usually getting something around the 1 meter is I think so a good compromise between speed and accuracy of the processing. So so the resolution is gonna have a big effect on the processing time. So if you're getting the resolution much more higher than your needs, well, the processing time is gonna be impacted. So really choose a resolution that fits your needs. And so yeah. Also, you can generate a point cloud at the same time of generating your surface model. So it's going to give you a last file that can be colorized later on with the images. And also, you can specify the overall vertical accuracy that you want to give to your model. So you can have a model that's maybe really precise, but the processing time will also going to be affected. So from there, also, you can extract a terrain model from the surface model. So basically, it's an algorithm that's going to try to remove as much as possible the elements that are not ground related. So it's going to remove houses, buildings, and all those other elements, and try to give you a smooth surface to do the ortho rectification if you want to do an ortho rectification directly from the terrain model. Also, you can do what we call a true ortho. So I'm going to talk this just in a few moments. But here the key part when you're going to extract your DTM is what kind of details you're getting to on your terrain model. So you can also use the DEM editing modules to get much more finer results on your overall DTM. But at the end, the main goal here is to try to see what amount of time you want to pass on the editing of your DEM. If you want to have a bit more information about the DTM extraction modules, I suggest you go see one of the webinars we did on that specific topic, and we're going to give you much more information about how you can extract a highly precise terrain model from your surface model. But now, if we look into the software and see how it looks, basically the first thing you would like to do when you're gonna extract your surface model is you're gonna open your project tree here, and you're gonna disable the two flight lines here that correspond to the multispectral imagery. So I'm gonna use here the little disable button, and then I'm only gonna keep the flight line number 1, which correspond to my panchromatic imagery. So from there, I will be able to open here the DSM generation. So by default, the software will generate an optimal resolution, which is 5 times the ground sample distance of the imagery. But you can also specify your own resolution here, and you can play with the vertical accuracy of your model. So in this case, let's say I could put it at 1 meter. And also you can generate a point cloud. The point cloud is optional, but the surface model will be generated into the SMF2 format, which then you can export it as a GeoTIFF file or an ASCII file. So once your surface model is extracted, you will have something like this, which represents the overall scene that we're trying to map. And from this scene, I can use the DTM extraction tool, and I could also input some 3D constraint, such as 3D break lines if you have priorly digitized them, or you can use some area, so you can draw some polygon and use them as an exclusion zone. So let's say if you have some areas that you have maybe bridges, or you want to keep some area intact in your terrain model, you can draw some polygons in the DTM editing modules and use them as exclusion zone, so those areas will be kept intact in your terrain model. In this case here, most of the edition that I did was here. We had a big water area, so I did do a polygon around this section just to remove this section, or I could have flattened out to a constant elevation, because usually water can create quite a lot of noise because of the texture when we're gonna match both images together. So now, producing orthomosaic from the satellite imagery. So we offer the possibility to generate 2 types of orthomosaic, what we call the classic ortho and the true ortho. So basically, the classic ortho is going to be an ortho-rectified images from the terrain model. So we're going to correct all the topography deformation and also all the camera and all the camera distortion from the terrain model. So you're still gonna have some what we call parallax effect in elements such as buildings or other elements that are not terrain related. But if you want to correct for such elements, you can do what we call a true ortho. So the true ortho is gonna be an ortho-rectified images directly from the surface model. So the acquisition and goal of a satellite imagery can have a big impact on the quality of the true ortho you can generate from, since the images are usually acquired off nadir. It can be challenging to have a really high quality true ortho. We usually recommend to do the ortho directly from the terrain model, because it gives much more nicer results. But you can also perform true ortho if it's your need. From your true ortho, you can also input some 3D break lines. So if you have, let's say, building roofs that are already vectorized, you can use them as constraint during the ortho rectification. to correct for other pixel displacement. One other thing that's important when you're gonna do the ortho rectification with satellite imagery is how you're gonna handle your folder within Correlator 3D, because the panchromatic and the multispectral doesn't have the same resolution. So what you would like to do here is you're gonna run one set of ortho from your panchromatic and then one set of ortho from your multispectral. So you're gonna have two different folders at the end. One with your ortho mosaic with your panchromatic images, and one with your multispectral images. And at this point, you're gonna have, let's say, your panchromatic here at 30 centimeters, and your multispectral at more than 1 meter resolution. And finally, if you want to, you have multiple scene imagery and you want to all tie your images together, you can produce a mosaic scene. But in the case where you only have one stereo pair, well, you don't really need to do a final mosaic, because basically the scene is the area you're trying to map. So the ortho can be your final product. So if I show you how it looks here, so first of all, you can see here in my project tree that in my ortho section, I have a little plus button, which is going to allow me to change my ortho folder. So the main goal here will be, first of all, to select your terrain model. And from this terrain model, you will be able to ortho rectify the images. So you can see here that since I have previously disabled my multispectral imagery, I have a resolution at 0.3 meters, which is basically the resolution of my panchromatic imagery. So from there, you can also specify here, you can crop your images if you only want a subsection. And the final imagery will be stored as a geotiff file. So we're going to produce one images for each of those two scenes. Then, if you want to ortho rectify your multispectral imagery, you're gonna have to go here into the ortho section, go on the plus button here, and then change the location or create a new folder where you're gonna store your multispectral imagery. If you don't do that, the thing is you're gonna overwrite your output from your panchromatic. So it's really important to do one folder for the ortho panchromatic and one folder for the ortho multispectral. So here what you can see is I did one folder for the ortho panchromatic, and I've created another one for the multispectral. And then once you have changed your folder, you will be able to disable your panchromatic images and then re-able here your multispectral imagery. And when you're gonna generate the ortho photos, well, I see that my resolution has changed, which is now the resolution of the multispectral imagery. So at the end here, the goal is to have two different sets of ortho photos. If you have then more than one scene to mosaic together, you can use the mosaic creation. So we're also gonna try to do a color balancing between the scenes to have a uniform color adjustment throughout the scene. And then this final mosaic will be exported as a geotiff format. So finally, the last topic of my presentation is how to pan-sharp your multispectral imagery. So basically, first of all, what is pan-sharpening a satellite images? What is the process behind? So basically, the process behind is to merge the resolution of the panchromatic imagery with the spectral information from the multispectral imagery, and at the end you're gonna have an images with the resolution of the panchromatic, but also colorized with the multispectral information. So the goal here is that you can do the Pansharpening. There's different algorithm of Pansharpening. What we use here in the house is we use GDAL Pansharpen to do the Pansharpening of the imagery. So the goal here is you will need to ortho rectify your panchromatic images, then your multispectral imagery, and from there you will be able to launch the GDAL Pansharpen algorithm from the GDAL library, and you will be able to have at the end Pansharpen ortho mosaic. So the goal here will be to select the same ortho and the same multispectral ortho from scene, and we're gonna take the input from the multispectral imagery and then merge them with the panchromatic information. As you can see here on the right of your screen, we have a result of a Pansharpening images. Once the all the photogrammetric and ortho rectification was done from correlator 3D. So again here, correlator 3D can bring you some unique benefits. So the goal here is that correlator 3D has unmatched processing speed. It has known to be one of the fastest solutions on the market. We also have different options for many type of users. So we have some solution for the people that want to learn photogrammetry with our automated workflow, but we also have solution for highly known or highly professional in photogrammetry that gonna give you all the flexibilities to play with the parameters within each model. We can process unlimited number of images within a single standard PC, and the solution can be integrated in a cloud approach such as AWS or Azure. And once you have a successful or a good workflow, everything can be batched from command line to have quicker results. Also, we offer a different flexible pricing. So we have different options for the monthly, the yearly, or the permanent options. We also offer different types of licenses. Today, the topic of the session was on the satellite image processing, but we also process UAV, medium, and large format imagery, and we offer the possibility of a node lock license on a single computer or floating license. So again, if you want to get started with correlator 3D, feel free to do a free trial from the website www.semactive.com, or you can also write us an email at sales@semactive.com, and we'll be glad to help you to find a solution that really fits your photogrammetric needs. I hope you have a great rest of the day. Thank you.